So the next question that has to arise is, what about the normal force? If it isn't equal to the weight, what is the normal force equal to? And does this change the force of friction? I know you probably see the answers coming just based on the structure of the questions. But let's take a look at this. If you would, please, draw another triangle. I drew this one going the other way. There's another inclined plane. We draw on that horizontal line so that we can measure the angle to the horizontal theta. I'm going to go ahead and draw in a mass. And I'd like again to draw in all of the vectors. So we're going to let that mass be m. Now acting straight down is going to be the force of gravity, mg. Go ahead, do it. I know you just did. Good. I'm going to let that be mg. The normal force is going to be perpendicular to the surface. And this time, there is friction, mu. So instead of it saying ignore friction, there is friction. So this time, there is friction. Now, if I look at a block sitting on an inclined plane and it starts to move, it's only going to go down the slope in this case, right? It would never be forced up the incline unless it was already moving or if it was attached to another force, another object. So I'm going to say that the force of friction is acting against the motion down the slope. Now, when I solve these problems, I have to go ahead and define which direction is positive. And I'm going to make perpendicular to the surface and down the incline my positive directions. I would even say that this would be my new x and y directions. Now, with that done, it becomes apparent that in order to sum up the forces, I need to break up mg into its components. So I'm going to make one vector perpendicular to the surface, and the other vector parallel to the surface. Okay? Those two components together are equal to mg. Now, if the angle theta of the incline with the horizontal is theta, then this angle up here is going to be theta, which makes the component opposite the angle going to be mg sine of theta. That is the force in the direction of motion that makes it go down the inclined plane. The other force that's perpendicular to the surface is going to be mg cosine of theta. It's adjacent to the angle. If you're not sure where I got that, rewind it and go back up to the problem above. Now, I purposefully drew the normal force vector to be the same length as mg cosine of theta. I knew to do that because I've done this problem like 5,000 times in my life, but also because I can see that the sum of the forces in the y direction has got to be equal to 0. The inclined plane is not going to cause the ball to jump off of it, nor is it going to break through that inclined plane. So those two forces on the incline have to be equal to each other. So if I say plus Fn minus this mg cosine of theta is equal to 0, then the normal force is equal to mg cosine of theta. Now back to work. If I look in the direction of motion down the inclined plane, I can say that the sum of the forces is going to cause the mass to accelerate. Now, I'm going to go ahead and call that forces, you know what? This time, I'm going to call them force parallel. It's just a different subscript. It just means parallel to the surface. I bring it up because different physics teachers write it different ways. No big deal. Now, in that direction of motion, the force parallel, I'm going to have plus, do you see it? Right there? I'm going to have plus mg sine of theta. That is making it go down the slope. So plus mg sine of theta minus the force of friction causes the mass to accelerate. I'll leave the parallel off at this point. Now, we're going to go back and play that same game we've been playing. What is friction? Yeah, that's right. Friction is mu times the normal force. And that causes the mass to accelerate. But what can I substitute in for the normal force? Yeah, you see it, don't you? It's no longer just equal to the weight of the object, but instead, it's going to be equal to mg cosine of theta. Now, that cosine of theta is just a number between 0 and 1. The smaller the angle, the greater the cosine of that angle is. So the normal force becomes greater. The greater the angle, the smaller the cosine is. All right. Yeah, I felt like that just resonated with a third of you. I'll take it. A third of you is good for now. So there's my equation. mg sine of theta, the force of gravity component that's pulling it down, minus the friction holding it back, causes the mass to accelerate. And there we go. We're going to split it up and do a couple math examples in just a moment with some real numbers. All right, so here's what I'd like to do. We've just talked about inclined planes and now inclined planes with friction. I'd like to do two examples where we plug in some numbers. The first one actually doesn't have friction, but it's an interesting problem. The second one does. Number one says, a cart of mass 2 kilograms is traveling up a frictionless incline with an initial velocity of 4 meters per second. If the angle of the incline is 37 degrees to the horizontal, what is the acceleration of the cart? While we're at it, what distance up the incline will the cart travel before starting to roll back? All right. So my first step is to do what? Yeah, that's right. Draw a picture. So I'm going to draw that the cart was traveling along on a flat surface and then started going up an incline. That angle is 37 degrees, and the cart was traveling at 4 meters per second when it first started going up the incline. Now, as it goes up the incline, there's going to be an acceleration. Which way would the acceleration be? Yeah, down the slope, wouldn't it? It would. Good point. All right. And then eventually it's going to stop, have a velocity of 0. So what's the acceleration? Well, what I'm going to do is draw in my vectors. So I'm going to have mg is straight down. The normal force is perpendicular to the surface. Now I'm going to go ahead and break up that mg vector into two components. Now they're at right angles to each other. Yeah, so I get to use right angle trig. And because the angle of the incline is 37 degrees, this angle up here in this triangle is also 37 degrees. So the component that is opposite the angle, I'm going to use the trig function sine. So that becomes mg times the sine of theta. The component that is adjacent to the angle right there is going to be mg cosine of theta. Now, before I can add up any vectors, I need to define which way is positive. And get this, I'm going to make perpendicular to the surface, but also up the incline as the positive direction. Yeah, I can do that. I can do whatever I want. I get to make the call. So do you. But the sum of the forces is going to cause that mass to accelerate in the x direction. We'll let x be the direction of the incline. Now, for forces, what force is acting in that direction? Yeah, there's only one. This component of gravity. And it's pointing down the incline, so I'm going to have minus mg sine of theta causes the mass to accelerate. Now, as we've already talked about, the mass in this case is going to cancel out, and I have an acceleration equal to negative g times the sine of theta. Now, anytime we're plugging into g with these formulas, we're plugging in the value of positive 9.8. So the negative sign in the front gives me negative 9.8 times the sine of 37 degrees. And I get, make sure your calculator is in degrees, I have 5.9, negative 5.9 meters per second squared. Now, to find out how far the cart travels before rolling back down, to me, that sounds clearly like a terrific trio problem, where the initial velocity up the incline is 4. The final velocity at the top, when it stops, oh wait, I said the word stops, it's 0. We're looking for the distance, and the acceleration is negative 5.9. Time? Don't know it? Don't care. So given that information, I would utilize the formula v squared equals v naught squared plus 2ad. The final velocity squared goes away because it's 0. So then I'm going to end up with negative v naught squared divided by 2a equals d. I subtracted it over, and then I divided by 2a. So I'm going to have negative quantity 4 squared divided by 2 times the negative 5.9. Let's see what we get. Anybody else get approximately 1.36 meters? Yeah? Good. Let's just back up for just a second. It's an inclined plane problem combined with a terrific trio. Is that legal? Heck yeah! The whole point of finding acceleration is to describe the motion. And how do we describe the motion? Terrific trio formulas. Ba-bang. Let's look at the next one. It says, a block with a mass of 500 grams is placed on a 2x4 piece of wood. The coefficient of friction is mu equals 0.25. If the piece of wood is set at an angle of 53 degrees, what is the acceleration of the block down the ramp when released? All right, first thing I'm going to do is draw a picture. Now I alternate the direction of the incline, just so you guys don't get too used to it. The angle is 53 degrees, and mu is given to be 0.25. I have a block M that has a mass of 0.5 kilograms. I often convert that right in my diagram. So now, what do? That's right, I draw in all of the forces. I'm going to draw mg straight down. I'm going to draw the normal force perpendicular to the surface. Now, you guys aren't drawing on a computer, so I'm sure yours will be perfect. And then I also have friction holding it back. Now, because mg is not going to be in what I define as my positive direction. I'm going to make perpendicular to the surface and parallel to the surface my positive direction. I just went, whoop. I tilted it. You see it? Tilt. Yeah. Or I could tilt my computer. Oh, now it's straight up. I need to take that mg and I need to break it up into components. So I'm going to do that. Every time I do that, I double check and make sure that that is perpendicular to each other and that the normal force is the same length right here as my mg cosine of theta. Okay. Oh, I kind of already let the cat out of the bag there. This component is adjacent to the angle, so it's going to be mg cosine of theta. This component is going to be mg sine of theta. So now, can we find the acceleration of the block? Yeah, of course we can. The sum of the forces is going to cause the mass to accelerate. I look at the force vectors in the direction of motion and I see two. I have mg sine of theta, which is pulling in the positive direction. I also have the force of friction, which is pulling in the negative direction. So let's do that. So I'm going to have plus mg sine of theta minus the force of friction causes the mass to accelerate. Now, I know that the force of friction is mu times the normal force. I also know that the normal force is equal to mg cosine of theta. So I'm going to substitute those in, and I usually do that in 2 steps. So first of all, force of friction is mu times the normal force. So I go back and I write it in. mg sine of theta, that's the component of gravity that pulls it down the incline, minus the friction causes the mass to accelerate. And in this case, because it's at an incline, the normal force is actually equal to mg cosine of theta, a component of the weight, not the whole weight, part of it, causes the mass to accelerate. So now, if I go 1 step further, got dark over there. I can cross off m. Now I can only do this because there's 1 m in each term. Divided both sides by m. And at this point, I think I have all the information. So I'm going to plug in my values. So I have 9.8 times the sine of 53 degrees minus 0.25 times 9.8 times the cosine of 53 degrees. Punch that in 1 step in your calculator. You got this, do it. No, seriously, do it. You got to practice. You can't just watch people sing. You got to sing. You can't just watch people punch things into their calculator. You got to do it. But I have an acceleration that I just calculated to be 6.35 meters per second squared. Yeah? Where we're going to go next with this, now that we've done a single one with terrific trio, now we've done an incline with friction, then the next step is to put it on an incline as part of a system with friction. Yeah. That's where we're going next. Thanks for hanging in there. We'll keep going.